this is one of the few spots in our country where they teach them together. And so Gregor, and within that scope, Gregor focuses a lot on the management systems and control systems. And he's had a few different positions in different a few different academic positions, and he also worked at Johnson Controls for some time in Germany. So with that, I think he's going to have a nice talk for us.
Yeah, I hope so too. Well, everyone, thanks for showing up on this beautiful afternoon. So today I'd like to give you an introduction to some opportunities for sustainable building design and operation that I've been involved in and that I foresee for the next few years. This is, as you can tell, possibly it's a shot of Boulder, but then on the left-hand side you see a few buildings that you will hear about again and throughout the talk, because these are case studies going back to 2005 and ever since 2005 when I spent a sabbatical in Germany on some of their high-performance building design initiatives. So the motivation for my talk today is that if we look at buildings in Germany and Switzerland from an energy intensity perspective, so that is energy consumed per square meter, square foot, primary energy use or source energy use per square meter in the building stock is on the order of, well, 400 air-conditioned buildings, 500 to 600 kilowatt hours per square meter in year. And in the United States, our CBEX data indicates that commercial buildings lie around here. Okay, so we're very comparable in the United States across all our climate zones. The motivation for doing better is that when we look at the most ambitious target to date for energy performance in buildings, people tend to quote the passive house standard, the passive house standard. And that approaches approximately 100 kilowatt hours of source energy consumption or primary energy consumption per square meter, which in US terms is 33 kBTU per square foot and year, if you feel better about that unit. And so if we look at some of these top buildings within a project known as NBAU, what turns out that these commercial buildings, a few of these commercial buildings have been able to meet that very ambitious standard, achieving reductions on the order of a factor of 4 to the building stock. And that's a very promising result, of course. Let's see if that works. So these high-performance buildings, and there's about 26 large commercial buildings that have been analyzed thus far, and this is not working because it's hidden somehow, I think. Yes. They tend to take advantage of two fundamental design characteristics. One is they rely on geothermal energy and on ambient air as free energy sources. Geothermal energies may be in the shape of near-surface ground heat exchange, so that would be the first 100 meters of the crust of the Earth that provides us with 120 meters of borehole heat exchange. We may rely on groundwater. We may rely on surface water. These could be rivers or lakes. The high-performance buildings also relied on ambient air for purposes of natural ventilation, as you can see here with operable windows, or mechanical ventilation through a air handling unit that's not shown here. And then we might reject heat by means of a cooling tower to the environment. So these environmental heat sources and sinks were used extensively in these buildings. And if you sort these, I have a group of about 19 buildings here. 10 of those use water-based cooling, 8 use air-based cooling, and 1 uses classical air conditioning. They are actually, those 19 buildings are, can be compared in their relative performance. Sizes ranged from a small 950 square meters to 21,000. This is this building. This is the Energon building in Ulm, which has is the world's largest passive house designed building. And air-based buildings between 1,000 and 14,000 square meters. The source energy intensities that were achieved are below 100, right? 32 to 100 kilowatt hours, 50 to 150. And here is the best designed, modern design air-conditioned building at a factor 2 compared to the others, okay? I have to maybe turn that table. I can't. That's difficult. Okay. The design features of these high-performance buildings are those used geothermal energy. They typically relied on so-called thermally activated building structures, which I'll talk to you about in a second, where we activate the thermal mass of the building directly through hydronic loops. Think of exposed concrete above you, which is activated through water loops, hot water or chilled water, or suspended cooling panels. The air-based cooling systems use ambient air for nighttime ventilation purposes to flush the building. These buildings use operable windows. Some use mechanical ventilation, and some use a mix of natural and mechanical ventilation. All of these buildings, even this one, had to have a high-performance envelope. Without that, you wouldn't achieve much. So if we look at the best-performing buildings on the left-hand side, those that have some form of ground source heat exchange system, that have some form of thermally activated building structure or concrete core conditioning system in their building. And we analyze the performance of these buildings in a little more detail. And let's do that here. Here you have shown here a ground source or borehole heat exchanger going into the ground by about 300 feet. And let's call that our boundary 1. And then boundary 2 includes that borehole heat exchanger, and it includes the heat pump or the chiller connected to that heat source and sink, the ground. If we then introduce the thermal storage and the energy distribution system and call that boundary 3, well, something's not quite working here for me today. Then we get to this point. And lastly, in the building itself, the ceilings heat and cool, and we call that boundary 4. So if we have these 4 systems from the source all the way to the heat and cooling delivery system, we have these 4 energy balances that we can look at the performance. And what we now simply do is we relate the amount of auxiliary energy that is required to provide that heating and cooling, that auxiliary energy, put it in the denominator, and the heating and cooling provided will be put in the numerator, and we call that the seasonal performance factor. So what you want is high levels of, or high values of seasonal performance factor, where you have little auxiliary energy required to provide a certain amount of heating and cooling, right? So if we compare these buildings, it turns out that seasonal performance factors, or efficiency, of a target value of 10 was what the design team was after. So high efficiencies, so you want high values of that black curve. And these are the 19 buildings I showed you. These are the same building. This is a school, a large school in southern Germany. And you can see over these 3 years, 5, 6, and 7, 2005 to 6 and 7, actually attained efficiencies of 10. And then you have a building that has a seasonal performance factor closer to 20. And you can see our air condition, our building with the conditioning system on the order of 3, so much lower seasonal performance factors. These are groundwater, rainwater systems. That's what the acronyms stand for. Now, if we pick out 2 buildings, 2 of the high-performing buildings, you have the large school and you have the Energon, that large passive house building. They're actually 30 kilometers apart, close to the Swiss border. It turns out that if you go from boundary 1 to 2 to 3 to 4, that the seasonal performance factor, your efficiency, goes from 10 to 5. So it drops by something on the order of 50%. Similarly, in the Energon building, we noticed the seasonal performance factor dropping from 17 down to 8. So the question was, what's happening in between, right? Why are we losing 50% or about 50% of the efficiency of that system? So the lesson that has taught us is that the system per se, or the environmental energy per se, isn't enough. It's all about integration. It's all about how you realize the project. And it has to do with sizing the systems properly. And it also has to do with operating the systems properly. Please, Igor.
We want to make
They are for
Is the seasonal performance factor
for these four boundaries.
four boundaries?
Yeah. So is this just the ground source system with the chiller, with the storage, and then the whole system? So the whole system then degrades quite significantly. And these are two of the best buildings ever built. Okay. So the conclusions we draw were that we can achieve these high primary energy performance or key performance indicators of less than 100 kilowatt hours of energy consumption. All these high performance buildings, all 19, showed that commissioning was necessary during the first 1 to 2 years, at least 1 year of fine-tuning the buildings before they worked well. It turns out that for these climate zones, a well-designed environmental heat source and sink is sufficient for heating and cooling. If you need to provide active cooling, you need to have a heat pump. But that was, if you need, if for cooling was without vapor compression, in all of these projects, I should have pointed that out, there's not a single chiller except for that last 19th building. The rest is cooled directly through the ground source heat exchange. And for heating purposes, you need a heat pump to elevate the temperature above the 10 degrees Celsius that we typically get out of the ground. The downside that was realized is that the performance of these heat sources and sinks are sensitive to poor design assumptions and poor implementation. So we realized that what we need are quality assurance tools. But another thing that was realized is that control of these high performance building is something that needs to be investigated. And that brought us to a look at the US building energy situation. And in the United States, we have about 95 quad of energy consumption, which is 95 times 10 to the 15 BTU. It's a British thermal unit. It's a funny unit. But anyway, of that pie, 20% go to buildings. And those 20% break down in this way. And now the question is, how much could we save through improved controls? And we find two sources. Lawrence Berkeley National Lab says you can save 3% through 3% of all of our US energy consumption, that is, through what we call retrocommissioning, taking buildings and improving upon them. Pacific Northwest Laboratory says we can save 1% of the US energy consumption through advanced controls in buildings. And so that doesn't apply to refrigeration, but it's the 1% I was trying to point out here. So we have, through retrocommissioning and through advanced controls, we have on the order of 3% savings potential of the entire United States energy consumption. So let's take a look now at at a building design. Yes?
That's 20% of the energy used in the building.
Yes. That's a good reference, yeah. If you take those two numbers and relate it to the commercial energy use, it's a much...
15 versus 5. 15 for retrocommissioning, 5 for
Yes,
control.
exactly. Okay, so what is the state of the art in building design today in 2012? So what we've learned is that high performance buildings tend to come with a few design features. So the state of the art, and that's my opinion, state of the art typically involves some form of ground source heat exchange system. It has a heat pump here that provides heating and cooling. It has a dedicated outdoor air system. The dedicated outdoor air system separates the ventilation loads for sensible and latent ventilation loads from the building loads. So we can focus on the ventilation separately with these systems. The building involves fairly massive construction with radiant heating and cooling systems. We have here in this floor, we have radiant cooling coming from the thermally activated building structure. So again, you have a layer of concrete above you that radiates, cools down. The ventilation air is provided through a displacement ventilation system. So you see the air coming in here and being delivered through the floor, either a raised floor arrangement or diffusers on the side. So you have small amounts of air. These are just the ventilation air. And this floor may be cooling, this floor may be heating. This is just an example. The return air is collected here and then conditioned again in this dedicated outdoor air system. The peaking boiler may be necessary just to make sure that if the heat pump doesn't have enough capacity, you can deal with that. So a separation of building and ventilation loads, a reliance on massive construction, the inclusion of environmental heat sources and sinks, in particular the ground where possible. All these things combined with high performance envelopes allow for a good performance of these buildings. So we took a building like this and we asked, okay, if that's the best we can do, how should we operate it? And the paradigm for operating such a building that we adopted is one that we would ask for the best possible operation of a building through a reasonable time period, and the reasonable time period is 1 day or several days in a row. And so the approach we have adopted is known as model predictive control. And model predictive control is an established control paradigm within the industrial engineering and chemical and pharmaceutical engineering industries. But in buildings, it's a relatively recent development. What does MPC do? MPC comes in 2 flavors. In offline MPC, I have a model of the building, which is this one. And I have this offline, sorry, this is offline. I have this typo. This should say offline. I have this model of a building, and I optimize the operation utilizing this model predictive control system. I come up with an optimal strategy, and I apply the optimal strategy to the model. So the model and the application domain are the same. So this is a simulation world, offline, right? We do this in simulation. In online MPC, I have a model of the building, and you can clearly see that the model of the building is not equal to the actual building, and you can see that through the fact that this building has a chimney, and this one doesn't. So these are necessary simplifications. So this model may be a 5-zone representation of a 100-zone building, or it may be a single-zone representation. It may have and will have simplifications, and it will have modeling uncertainty involved. But I now use the model of this building to come up with a strategy, and I apply this strategy to this optimal strategy, U star, to the actual building. And if anything, I get a state feedback from the building. I get a state feedback from the building, that's X, and then I do this in a continuous fashion. This is what we call real-time model predictive control, or online model predictive control. I have a model, I have an actual building, and I'll show you an example of both applications. You just should keep in mind that there's an offline analysis, which is the ivory tower, and then there's a real-time online implementation of this, okay? So we can learn something from both implementation. So how does MPC work? Well, in brief, we start with a model of the building. We initialize it, and then we basically have a horizon that's known as the cost horizon. In that cost horizon, we have a planning period and a termination period, and we come up with an optimal strategy over this horizon while accounting for the cost occurring in this horizon. This strategy we then execute, and once we have that executed, I need a new battery. Once I have this executed, I now begin the process again and plan a new strategy. And you can guess what happens. Now, this is my initial state. I plan a strategy over this horizon, and that solution becomes the new execution. And indeed, this just continues ad infinitum until the end of time. In an offline scenario, we've implemented this using a model representation. I told you that we need a model, and the model we have adopted for our work is represented in a program, or in a simulation program known as Energy Plus. Energy Plus is one of the widely used building simulation software packages. It's actually funded by the Department of Energy, and it is heavily supported right now, and I think it's the tool of the future. Okay, in an offline MPC environment, we wrote an optimization environment in a programming language known as MATLAB. We create an input file, we read the input file, when we generate a candidate of a scenario, we prepare the corresponding input files for that scenario. We simulate that using Energy Plus. And from Energy Plus, we then get results. And we check whether or not this result meets our exit criteria. And if it doesn't, we repeat. And we go around the merry-go-round here for a while until we find a solution. And once we find a good solution, we save that output. Okay, once we found a good solution, we then step forward and we repeat the process. And this is what gets us through time, allowing us to find solutions. Okay? Oops. I'm sorry, my mouse left me. Okay, so let's look at one of those high-performance buildings with a thermally activated building system. And it's a 3-story building model. And in this offline investigation, we look at a building that has a dedicated outdoor air system, DOAS. It has a sensible heat recovery ventilator with heating and cooling coils. We needed 4 heat pumps because Energy Plus doesn't have a reversible heat pump model, so we needed 1 for radiant heating, 1 for radiant cooling, and 2 more for the DOAS. We prevented the radiant heating and cooling to occur simultaneously, and what this gives us is a reversible heat pump model in Energy Plus. We then assumed this building, the 3 stories, to have 11 zones, and each of the 11 zones has a constant volume radiant hydronic circuit, which means water, right? A water circuit with a pump that runs at a constant speed. And the cooling and heating set points are according to a comfort standard that is used in Europe. It's similar to our ASHRAE standard 55. It has similar temperature set points. And the way to control these buildings, there's a lot of work done by famous researcher in our field, Bjarne Olesen, and he published a lot of work on this, on how these buildings should be controlled. And he came up with so-called heating and cooling curves, separately for heating and cooling. And recently, Siemens Corporation has developed a very elaborate system known as the UBB method, the unknown but bounded control method. Manfred Morari was involved in that too, and he's at the ETHZ in Zurich. And so they came up with an improved control strategy for these thermally activated building systems, buildings that have a lot of mass and are slow to respond. And so what you end up with is a separate heating and cooling curve for each of the zones. So the optimization, and I'm just want to summarize, what can the optimizer do? It can turn off and on the pumps for the radiant system. So we have a radiant pump availability we can manipulate, and the temperature of the supply water into the radiant ceilings. Okay, those can be adjusted. The pump availability was modeled as a so-called pulse width modulation control in 10-minute increments. The supply water temperature was bounded, and every day was broken into 4-hour time blocks so that we made a decision for each 4-hour time block. If we could have done this for 24 hours, it would have just taken longer, and we would have had more granularity and longer run times, which were long anyway. Now, if we just wanted to minimize energy, then what would you do? You'd never turn the system on, right? So in order to prevent that from happening, right, in order to prevent people from freezing or being overheated, we had to introduce consideration of comfort, and we did that through a term called misery, right? How miserable are people in the building? And the misery term has to do with an index used in our industry called predicted mean vote. So whenever that, so what you get basically is energy, and you get that comfort penalty P, which is a misery term, and the sum of the two are to be minimized. What this means in practicality, so I'll skip this, but what this means is when the building is within a PMV band of plus minus 0.5, then everything's fair game, everything's good. And if the optimizer shown in gray is better, closer to the 0 than the base case, then that's fair game too. But in this scenario, the optimizer chooses a comfort outside the allowable range. So that's red, that's bad, and this is bad. And moreover, if the optimizer chooses a comfort setting in the building that is worse than the base case, then that's bad too. So you can be within the band of plus minus 0.5, but you can be outside the band if your base case is worse, but you cannot be worse than the base case outside. What we found is that the optimizer chooses interesting strategies. So this is the building temperature. This is Saturday, Sunday, and this is then a week, Monday, Tuesday, and so forth. First thing we notice is that the optimizer maintained the building at a cooler temperature, about 2 Kelvin cooler. And you see two pairs of temperatures. One is air temperature, the other one is known as operative temperature. Operative temperature is the more meaningful temperature index for buildings because it recognizes the effect of radiant temperature on occupants. Yeah, that's model. This is offline modeling data, okay? What we see is the optimizer chooses cooler temperatures and about 2 Kelvin cooler. We see from an operation perspective, the standard building are these circles. These are the supply water temperature of the standard control, the Bjarne-Olesen control. And the optimizer, you can see, chooses much lower temperatures. These are the blue X's. These are the optimal supply water temperatures. So instead of heating the building with 25-degree water, it is actually operated with 18-degree water. So what we see are the optimizer runs the building systems, the HVAC systems, much more restrictively and at lower temperature. And the effect is, if you compare them against each other, in the standard operation, we have this is energy consumption for a range of energy uses. You can see red is heating, blue is cooling. Red is heating, blue is cooling. So under standard control, the building constantly oscillates between heating and cooling. It heats, it cools, it heats, it cools. The optimizer, you can see down here, basically achieves large savings because it much less frequently runs the circulators, the pumps, and has much smaller heat pump loads. So this is base case, this is optimized case, and you can clearly see the differences. If we now subtract this from that, you get the savings, and you can see all these avoided heating and avoided cooling that's occurring here. But what I think is most interesting is that the MPC results indicates that the optimizer does all that by keeping the building more comfortable. Because the comfort range is that plus minus 0.5 PMV range, and the blue PMV lines, or the blue optimal control case lines, are actually never outside the thermal comfort. So what we see here is that the optimizer has a chance of significantly reducing energy, all at the same time providing better comfort than a normal building would. So that's what we think is quite promising. So we noticed in comparison with the Olesen and the unknown but bounded method that the optimal control approach finds better solutions. We did end up, however, recognizing that Energy Plus is exceedingly slow for these kinds of analysis, and we had to wait for a long time for the results to occur. So this shows an application of offline MPC utilizing simulation. Now we took the same system into actual buildings, and in this online MPC sequence, which looks similar to what we did earlier, I apologize. In this online MPC system, we now have the optimization on the right-hand side, and we get weather data from National Oceanographic and Atmospheric Administration. We create an input file, and then we do the same process as before and get a result. Now, what we do with the result is we first store it in a database, and then we send it to a building. Okay? So we optimize, find the best solution, store the result, and send it to an actual building. And the building takes it on and implements it, and next time that we repeat the process, we get more fresher data, fresh weather data, fresh other sources of information required, and then repeat the process. And so one approach of implementing that is as a cloud-based software as a service. So here we have the cloud. So 4 years ago, we developed this, or started to develop this, where we take weather data from NOAA, we take electric utility data from trading desk or from the energy provider directly. We get the pricing data. We feed this into this network operating system together with the weather forecast. And we have the optimization running here. The optimal set points are sent to the building. And the building accepts them through an open access, open interoperability platform called Niagara Tritium, which allows us to put a, you can think of it as Java for buildings. It's a layer on top of any legacy building control system that we put on top, allows us to reach into any building. It doesn't have to have a particular vendor of building automation system. It could be a Johnson Controls, Honeywell, Siemens, Automated Logic, whatever system, and this would work. And here's a day where that I wanted to show to you. On this particular day in Chicago, the temperatures were all the way up to 90 degrees Fahrenheit. It's in September, I believe. September day, that's what I recall. And in blue, you see the prices, which we call the day-ahead price. So the day-ahead price, a day before that day, this is what was predicted to us, this blue line, in terms of electricity pricing per megawatt hour. And that's equivalent to 2 cents a kilowatt hour, and that's equivalent to 6 cents a kilowatt hour. The next day, when the actual following day, the prices were not as predicted. Sometimes they were lower, and sometimes they were higher than that day-ahead pricing. In fact, you can see an interesting, you can observe an interesting artifact down here. You see negative prices here in the middle of the night. Does everyone see that here? So these negative prices actually do occur in the Midwest. This is PJM territory. This is around Chicago. This is when in the middle of the night you have throttled down all your coal-fired power plant to the minimum, and you cannot turn them down any further unless you turn them off. But you can't turn them off because you need them again 5 hours later. So that's why prices go so low that you say, please, someone take my power now, because otherwise I have to turn off. So these are very common effects, especially in May and June in PJM market. Prices sit down here. I don't think we'll see much of this in the future because we have less and less coal-fired power plants on the grid in that area. We have more and more gas-fired power plants coming online. But now we have an actual building, and this is actual data for this large commercial building. So this is a building in the loop of downtown Chicago. It's about 1 million square foot in size. And what you see here, oddly enough, are 48 half hours. So please, this is one day. So 24 refers to noon. Now, the ComEd peak demand period for the supplier was between 9 a.m. and 6. Is that correct? Yes, that's 9 and that's 6 p.m. exactly. Between 9 and 6 p.m. the peak demand period occurs. So the building was, the strategy that the optimizer came up with for the September in 2010 looked like the red line here. It started the system at 4 a.m. You start pre-cooling the building, and it basically predicted the consumption pattern shown in red here. In reality, we have observed electricity consumption shown in black here. And you can see a very good match. It's actually not necessarily easy to get to that kind of a match. The beauty of a model is we can go back and say, what would have the calibrated building model done if we hadn't done any pre-cooling, right? If we hadn't applied optimal control. The building would have started at 6 a.m. instead of 4 a.m. It would have come up and then would have experienced a very typical afternoon peak in electricity consumption. We see that in many buildings. And if you look closely, you can see that the difference achieved is on the order of, well, that's 1,800 kilowatts down to 1,300, something like that. So we have about 500 megawatts of energy stored or demand response achieved during that operation. So the peak energy was reduced by, the peak demand was reduced by 25%, and 24% of the on-peak energy was moved outside to morning hours. And this optimization approach allows us to consider not just cost of operating the building, but we can also look at the energy efficiency. We can say, please operate the building in a way that accounts for cost of operation as well as efficiency. Or please only focus on peak demand. Tomorrow I'm only interested in tunneling through 1,200 kilowatts of demand. Help me achieve that. The optimizer could do that and would find a strategy that allows you to go underneath. The concept of model predictive control also allows us to say, whatever you do, don't turn on and off your chillers more than 3 times a day, because we can't afford the maintenance cost or the chiller will break, so we can put in chiller starts and other things. So the fundamental idea behind this is we have weather forecast, current zone temperature, outside temperature, we have pricing signals, we utilize a calibrated model and then come up with optimized operating schedules and temperatures and suggested or predicted performance forecast. Now, you all saw the prices peaking at about $60, $70, $80 a megawatt hour. Just for your information, last summer in 2011, this is what we observed in Texas. I'm not sure if anyone has followed this. Does anyone know that Texas is the only state in the country that has its own regional transmission organization? It's completely separate from the rest of the nation and kind of goes along with Texas, right? So Texas... Yes, exactly. So you can read, there's not a power line crossing Texas to Oklahoma, right? It's complete island. Now, do you remember the numbers I showed you earlier, $60, $70, $80? Where would that be? Oh. So look at 2011 in Texas. Look at what an incredible problem they had in terms of providing power to their customers. It was a hot summer, and did it look any better in summer 2012? It actually looked worse. In 2012, they capped the price at $4,500 a megawatt hour. So that's $450 a kilowatt hour. Would anyone like to pay $450 a kilowatt? No. Okay. So the interesting thing is that the day-ahead price shown in red, DAP, the day-ahead price in red was, look at this, 1st of August, was $300, and the real-time price went to $2,400. That's a factor 8. Day 2, the day-ahead price forecast was $350, $3,000 in reality. What does that mean? The system wasn't used to that kind of dynamics in the price, so they didn't learn quickly enough. And it took 3 days for them to actually recognize, maybe tomorrow we were going to have very high prices again, and the day-ahead price went up to $1,800, but it hit $3,000 again. So it took them a week to learn that. And then over time they got better, and you can see there are better matches. So the technology allows you to, or the idea behind this MPC allows you to curtail the electric demand of a large commercial building to tunnel through demand constraints and respond to these grid pricing, or to respond to grid pricing signals. So how different are these strategies from one day to the next, we asked ourselves. And so it's a little colorful here, but these are 3 weeks. And these are, I think, 5 days, Monday through Friday. So these are only work weeks. And you see down here pricing signals. Green is the one with the highest peak in the afternoon and the lowest low in the night. And that's consistent throughout. But these are different actual pricing strategies. So this is what customers see and would pay for the electricity. Now the question is, how does the strategy differ? And the thin gray line is the outside air temperature going up to 90 degrees or above 90 degrees. So it's a hot, humid summer in Chicago. And you can see, if I may pick out this day, this Wednesday, where the optimal strategy is actually very similar and fairly independent of the pricing here. It chooses a pre-cooling strategy up to 72 degrees. And on other days, let me take the Tuesday and then the week after, you can see the strategy being quite different. So here's a strategy where I have a deep pre-cooling down to 68 degrees. This is taking the building down pretty cold. Whereas with the next volatile or the next pricing strategy, I only pre-cool it to 72 degrees. And at the lowest pricing structure, with the lowest load shifting incentives, I do the least pre-cooling. So if you then ask, okay, if I just looked at not time but one particular week, and I think I took the third week, and I just looked at the impact of price, and you can see that from one pricing structure to the next, the strategies are vastly different. Sometimes they're, or not vastly, but they are different. So the question arises, if I knew how to run the building and applied the same pre-cooling strategy every day, such as at 4 o'clock in the morning, start to pre-cool. And that's then shown here in the dashed blue line. Here you see coming down here. Is the optimal control better, or how much better is it? It turns out that it's better every time. And if you take that 4 a.m. in the morning pre-cooling heuristic, depending on the day of the week for a particular pricing strategy, you can outperform that simple heuristic every day. It's just the degree of outperforming it is different. So this basically tells us that with online MPC, we can control a building in a way that responds to the current weather conditions and the current grid constraints and grid pricing conditions. So we do find some challenges, however, when applying online MPC. We found over and over again speed to be a problem. So we have relied on forward models, complex building simulation programs, and we have believed that complex phenomena require complex models. So we realized that the Energy Plus program that we've been using for this purpose hasn't really been designed for the purpose of control. It has been designed for the purpose of designing buildings, right? Using it once in the life of a building. So how do we get around that? How do we get around this problem? And for that, we have come up and started to investigate a new approach, which is relying on offline MPC and utilizing what we call rule extraction. So what we do is we have a model, a building energy model, and that building energy model we now exploit in an offline ivory tower simulation MPC approach. We get results, optimal results, and those optimal results we then use in a supervised learning context. And in that supervised learning context, we can either use discrete problem classification or regressions using continuous variables. So we have classification and regression techniques we can apply to the optimal results. And now we take these optimal results and we test, we take the optimal results, we apply these supervised learning techniques, and we test these new strategies, simplified strategies, much simpler, on our simulated model. You see, it still doesn't have a chimney. It's still the simulated model. And we start with open loop testing and then go to closed loop testing. I'll tell you what that means. So once all this is done, the idea is to take this control strategy, the simplified control strategy that we have extracted as a rule, and implement it as a control logic in an actual building using a building management system or building automation system currently available. Okay, so we have discussed the upper part, the model development, the offline MPC, the ivory tower work. We've seen the great results that has provided, 56% savings. I should have pointed that out in some cases. Now let's take it into the rule extraction mode. The supervised learning techniques that we've used, data mining techniques, and that have worked well to various degrees are so-called generalized linear models. The other one are classification and regression trees, CARTs, and adaptive boosting techniques. What is a GLM? A generalized linear model looks like a linear model, so it has parameters beta, parameter vector beta, beta 0, and then these betas here. And what we have are these regressors that provide us with a prediction of that variable theta, and that we use in an inverse link function to get us back a probability of action. So we have a logistically linked model. This is our logistic function as a link function, and we basically get a probability of action. And the probability of action may vary between 0 and 1. And then we set a threshold of probability and act on that. The wrong direction. The classification and regression trees look like this. They basically, if outside air temperature is less than 24 degrees Celsius, then, and that's yes, then go down to the left. And then if the zone temperature is greater than 24 and the answer is still yes, then open the window. So what we have are these decision trees. These are called dendrograms. And you basically can start at the top and walk yourself down, and you get fairly simple rules as the outcome of that cart model. And this is just a representation of that decision tree over there in terms of outside air and zone temperature. And you can extend this idea in a simplified way. You can extend this idea to basically use stumps of classifiers and have these many classifiers vote. And then if you look at the vote of many classifiers, and that's greater than 0, it's positive, then you vote yes, or if it's negative, then you vote no. And that then tells us what to do, open and close a window or set a certain temperature set point. The rule extraction, and I think in the interest of time, I'd like to take a step forward here. We test in an open loop and a closed loop fashion. Open loop is the best possible performance, where we basically predict the control vector in advance and the states are present during the optimization. In a closed loop fashion, we embed the rule in the energy model and evaluate it every time step so that states change and errors that we have may feed forward into the simulation. They may impact the next iteration. That's a much more real-world performance. So the closed loop, in a nutshell, the closed loop analysis of our rules is a more realistic assessment of the quality of our rules. Now we go to a little building like this, shown on the left. It's in Boulder, Colorado. It's a mixed mode building, so it has, does anyone know what a mixed mode building is? A mixed mode building is one that has classical HVAC system, but it also has natural ventilation and operable window features, okay? So the question is how to control the window opening to minimize energy consumption. How should we open and close windows? And the window the MPC, the model predictive control results for window control, basically says this, okay? So this is ambient outside condition. This is window open, open, close, open, close. So this is the MPC optimal result. You can see that the MPC approach basically exhibits a night ventilation pattern, exploiting the passive thermal mass in the building. And if you look closely, the optimized case sits here in terms of HVAC or electricity consumption. It sits under the base case. The base case is dashed. The optimal is solid. So we see savings, and we see the savings during the peaks of the day. So we have reduced peaks in cooling and therefore reduced electricity use. So this is what we get from the MPC. And now the question is, can we learn rules from that? And we looked at various regressors or predictors here, excuse me. We looked at the outdoor dry bulb temperature, the dew point temperature, wind speed, wind direction, where's the sun, how strong is the sun. So we looked at a range of independent variables that could help us classify and or arrive at control rules for this problem. And what we found is that utilizing this set of variables, we were able to come up with a generalized linear model that achieves 91% of the optimal savings. So the optimal savings are shown. The optimal savings are shown here. Savings. Yeah, this is savings. And of that savings, in the open loop design, in the open loop test, we saved 91 or 90%. So that looks very promising, but we realized that as soon as we took the rules and applied them in closed loop fashion, we only achieved 11%. So the rule really breaks down once we put it into place. Whereas the cart, we looked at several cart models, that second cart model was showing 88% of the optimal result in an open loop and 84% in a closed loop fashion, which means that the optimal result that I get from an offline simulation or optimization, I can maintain about 80% of that and implement that as a rule. And the adaptive boosting techniques outperformed this, but there is a reason for us that we preferred the carts, and I'll try to explain why that is. And The cart structure that we got, a cart is shown here, shows that we have, this is again one of those dendrograms, and this up there means is the temperature in the second zone in the middle layer greater than 19.7 degrees. So through the supervised learning or data mining techniques, we came up with a dendrogram which has 9 splits, so 9 if-then-else statements, and it basically guides the optimizer to open and close windows based upon zone temperature thresholds. And so these are, we also saw very small dependence on ambient conditions, so this is trained on a particular set of data, so we say don't apply outside these training conditions, which is the problem by itself, but we get a fairly compact representation of this. And if we put the two together, the optimizer window opening is shown up there. It says when to open and close window. And the dashed line is that probability of opening the window, right? And we let's just focus on the solid line. You basically see very similar trends in the open loop response, and you can see different trends for the closed loop response, which tells us that there is still there's still work to be done to maintain robustness. So the open loop response is very close to the optimizer. We only have 16% misclassification. And unfortunately, in the closed loop response, we often miss nighttime openings. Okay, let's skip that. So the question is, why do we prefer these classification regression trees? And the reason is because we want it to be implemented in real buildings, right? The logic tree that you saw is concise. It's easy to interpret. We can take a cart model and interpret that or encapsulate that in a building automation code in just a few lines of code, and we need to be able to convince these people that actually run buildings that this is a good idea. So we have seen promising results replicating these binary window opening MPC sequences. The closed loop test we consider to be the more important one to actually determine whether or not the system works. The boosting models provided the overall best performance, but we think that the cards are the best real-world choice. Okay, in the future, we need to consider sensitivity analysis of these extracted rules. How well do they work under changed conditions? Can we generalize them to other classes and other types of buildings? Are there other supervised learning techniques that we didn't consider thus far? We have not yet implemented these rule extraction techniques. The online MPC techniques we have implemented, and they work. And then lastly, what I consider most important is how do we account for stochastic influences? Actual people occupying actual buildings. And I know I'm coming to the end of my time. I just wanted to point out that we are looking at this issue of occupant behavior right now in a different project. And in this project, we're looking at considering uncertainty in occupant behavior. And we're trying to implement that to find optimal strategies in the face of uncertainty in occupant behavior. And the field implementation of that, I skip here for 2. The field implementation will look at the same idea. First, we begin with so-called stochastic model predictive control. And the stochastic model predictive control gives us time series results. From these, we then derive these carts, these classification and regression trees. We turn them into computer code, and then we implement them in buildings. And the buildings we have, we get these distributions. I will skip those. The buildings we work on right now is the Y2E2 building. That's next year. The research support facility in Golden, Colorado. We implement stochastic model predictive control right now in this building. And next summer as well, we're going to go into the sustainability base at NASA in San Jose. So there are some interesting, these are some interesting, definitely high performance buildings. This is a mixed mode building. This is a mixed mode building. So people can open and close windows here and here as well here. And so the question is, you have these phenomenal building designs. How can we achieve their best potential once they're built? And what I hope to have shown you today is some approaches utilizing advanced control that once you even have, or once you have arrived at a good model, how can you take it basically through its 5 to 10 decades of operation in the most energy efficient fashion. So with that, I'd like to say thank you for your time and attention, and open for questions.
Thank you, Gregor. Is there any questions?
So, the emphasis relies on the use of Energy Plus, or any other,
It actually,
or any other model?
so this is a yes. So we have Energy Plus, and we have recently started also looking at faster reduced order models in lieu of Energy Plus that rely on operational data. So we have operational data in many buildings. We train reduced order models and use those.
How much do you see the results depending on the calibration of the Energy Plus? And this topic is technical.
Yeah. It's a big topic. So calibration of the building energy model. So if we do model-based control, I told you tongue-in-cheek a bit, but the difference of the model didn't have the chimney that the actual building had. Well, in reality, we talk about a large number of potential differences. And how do we account those, or how do we observe those? How do we introduce them into the model through calibration? I think calibrating internal gains in particular we find, which is hard to measure, right? Internal gains in particular are important to capture properly. So you want the simple answer is you want the best calibrated model you can achieve with the given dollars you have to gather data, right? So,
You've seen good performance with Energy Plus calibrated just on the early data.
My question was going to be a little bit like the opposite. Have you ever, so I think in all of your talk you kind of said that model-based control or management of buildings is a good thing.
I try to, yeah. Mm-hmm.
Yeah, so do you have any cases where even a bad model, or even whatever model will make it worse than a baseline? Or is it always in the positive? Even if you have a really terrible model, maybe it doesn't get you as optimal as you could get with a better model, but it gets you better than the baseline.
Wow, it's a very deep question. So So we observe in the real time, the online MPC work, we look at a number of metrics to make the decision, is the model in tune with the actual building? But the matter of the fact is, once you have a model and you derive a control strategy and you implement that control strategy, you have changed the way the actual building is operated, and you cannot go back and say, let's repeat the last day without the intervention. So that problem persists, right? So I cannot truthfully answer whether there are situations in which the error introduced through using a imperfect model suggests the optimizer find a strategy which is actually worse than would have found if I had not done any optimal control at all. So it's a very good question, but I can't answer that with certainty. Mm-hmm. Yeah, you could, yeah.
You can find a counterexample.
Well, there are bound constraints on the temperature, right? We do see the bound constraint on the temperature. But let me tell you this. We have recently, one of the buildings that we have done model predictive control on is the Sears Tower in downtown Chicago. It's 4 million square feet. It's known now as the Willis Tower. It's one of the world's largest buildings, and still today I think the largest commercial real estate building other than the Pentagon in the United States. And we have controlled this building over the last summer, 2012, using MPC, and we had the property managers allowed us to basically take control, not of the entire building, but I think it was about 1/3 of the building that we controlled out of 105 floors. And we were able to compare comfort, temperatures, and we were able to compare roughly, of course, because we changed the building dramatically through the control, to previous years. And the building has, the building has saved significant amounts of dollars and energy by running the building in a better fashion. So I think we didn't screw it up that badly. So they really liked what we've done with the Sears Tower. But Brian, you asked a really good question. You don't? Oh, too bad. Because at the beginning of class, she said that her heart is in energy efficiency and building efficiency. And she was looking forward to the talk, so I thought you might have a question now. Okay, well then, if there's no further question, I'm here. I'd be glad to take some more questions right now. Otherwise, thanks for coming today, and it's been a pleasure being here. Thank you.